So Euclidean geometry, as I mentioned weeks and weeks ago now when we started doing this, the key to this topic, I mean, there's not many new theorems that we're looking at. What we really want to be working on here is our setting out, our explanation, and what have you. So let's have a look at the quadrilateral family. Bit of a family tree there. Always good to know where we came from. But all quadrilaterals can be classified, of course, according to the different features they possess. And just like any classification tree, the more features you know, the better you can classify the object. So as you branch down, the quadrilateral in this case becomes more and more specialised until you get down to, I guess, what we could call the perfect quadrilateral, that being the square. So any property you know about a particular quadrilateral can be used with any quadrilateral that branches off it. It will also have those features. Okay, so example, a rhombus branches off a kite. It also branches off a parallelogram. And for that matter, you can trace it back to the trapezium as well. So any feature of the trapezium, the parallelogram, the kite, or even just the basic quadrilateral, could be used in a rhombus. In fact, the classic one is the area of a rhombus, because the formula you use for an area of a rhombus is not actually the formula for an area of a rhombus. It's actually the formula for the area of a kite. But because a rhombus branches off a kite, we can use that formula. All right, let's break it down. Quadrilateral. So all we know about the shape is it has four sides. Not real interesting, really, but okay, if it's got four sides, we know it's a quadrilateral. It also has four angles. Okay. I suppose that allows us to use angle sum of a quadrilateral 360. But other than that, really, there's no specific properties. Okay. Let's branch off. I'm going to go over to the kite. The kite is the one where it has adjacent sides are equal. So basically you've got two pairs of adjacent sides being equal. See that? We know it's a kite. And so if it's a kite, what do we know? We know diagonals in a kite are perpendicular. Okay. So that's something we can use. And as I was saying, the formula for the area of a kite, half xy, where x and y are the length of the two diagonals. Okay. Branch off another way, we can come up with a trapezium if the fact that we know about it is we have one pair of sides parallel. What do we know about trapeziums, or trapezoids, sometimes people use as the plural? Well, pretty much just the area formula. So half perpendicular height times sum of the parallel sides. That's the formula we use for that one. Okay, but branching off our trapezium, we have parallelogram. Because parallelogram is, of course, now when we have two pairs of parallel sides. So you could, if you wanted to, use the formula for a trapezium area, if you wanted to, if you knew the information. Opposite sides in a parallelogram are equal. So there's a new feature that we know. It also means opposite angles in the parallelogram are equal as well. We also know that the diagonals in a parallelogram will bisect each other. And we can refine the formula by simply saying base times perpendicular height. Base times perpendicular height. And by the way, if you want to prove a shape is a parallelogram, then you don't have to show two pairs of parallel sides. Right? If you just look at one pair of sides and they're both parallel and they're equal as well, well then that's enough to say the shape's a parallelogram. Because it couldn't possibly be anything else. So if you have to prove it's a parallelogram, yes, you could go and show two pairs of parallel sides, or you could show opposite sides are equal, or you could show opposite angles are equal, or you could show the diagonals bisect each other, but there is that additional one that you could just look at one pair of sides and show they're both parallel and equal. Okay, kite, parallelogram. Branching off the parallelogram, we now have rectangle. So we're taking a step further where now the angle is 90 degrees. And you only really need to know one angle is 90 degrees. If you know it's a parallelogram, you got one angle 90 degrees, that's enough. You don't have to go and show all four, because of course all our parallel line theorems, you could prove they work quite easily. So it's enough to say, okay, I've got a parallelogram, one of the angles is 90, therefore it's a rectangle. But diagonals are equal in a rectangle. And again, we can refine the formula a bit more and say, well, length times breadth for a rectangle. But as I was saying, rhombus branches off both the parallelogram and a kite. So it has those features, but it also has this feature that we know that the diagonals in a rhombus will bisect the vertex. So they'll always bisect the vertex. And then we get to our perfect quadrilateral. It's both a rectangle and it is a rhombus as well. It basically has all the features of all the quadrilaterals, and I suppose we could have a formula for area if we really wanted to. It's the side squared, hence the square. Okay, I'm not going to bother with any examples of what have you. So D, E and F are the exercise that are all on quadrilaterals.